Hello everyone, welcome back to another session on Communication System 2 course. In this particular session, we will understand the bandpass sampling theorem and reconstruction of the original signal based on its samples. In the earlier sessions, we have understood the translation or the upconversion of original information signal, which we called them as low-pass signals, to bandpass signal in order to match the spectral characteristics of the channel. Now we need to understand the sampling of bandpass signals, because these are the signals which are received at the receiver when they are traversed through the channel from the transmitter end, and these signals when they are received at the receiver are to be again converted into digital domain to process further. So we need to understand the sampling theorem on bandpass signals. We have understood the sampling theorem on low-pass signals in your earlier course in form of Communication System 1. Here we will understand the meaning of bandpass sampling theorem. Further, we also need to understand how we can reconstruct the signal back based on the samples generated. Okay, let us take a bandpass signal, a real bandpass signal, x of t. Okay, x of t is a real bandpass signal whose bandwidth is b, as depicted in its magnitude spectrum here. So where x of f is its Fourier pair. Okay, so let's try to build a few relations between the parameters here, because we need to understand the meaning of all these parameters which I have depicted. So fc is the center frequency, need not be center, but eventually we take it as center frequency, which is a carrier frequency, which is half of fu plus fl, as well as the bandwidth b is the difference between the upper frequency and the lower frequency. Okay, so with this basic relation between the several parameters here, we will try to understand the sampling of bandpass signal. Now we have three options with us to sample a bandpass signal. Okay, so what are those options? There are options available to us. The first option to sample this x of t is that we can simply treat this x of t as a low pass signal. Okay, because we understood the sampling of a low pass signal in earlier course, and we can apply the sampling rate as and sample this signal at a rate of twice of fu. Right, so that was your Nyquist theorem, where we just took the samples at a rate of twice of its highest frequency component. The highest frequency in this case is fu, so we can just sample at a rate of 2 fu in order to sample this bandpass signal. But you should note that fu is a very high frequency. Okay, so fu is much high value, and hence sampling at a very high rate would cause a load on ADC. Okay, so this is a high rate sampling. This is a high rate which would make our ADC complex. Okay, so we can safely eliminate this option by noting that we cannot apply this sampling rate. So based on Nyquist theorem, we have another option with us. So we can sample x of t at twice of b samples per second. Okay, so this is again using Nyquist theorem. Okay, let's see how this Nyquist theorem can be extended to bandpass signal, and after getting the samples we'll see how the signal can be reconstructed faithfully or not. Okay, so that's the second option that we would be starting our discussion today. Okay, so the third option is that we will also understand another important theorem on sampling of bandpass signals by answering a question that are there any sampling rates between these two extremities, between 2b and 2fu. Okay, we'll try to find out such sampling rates which would constitute our bandpass sampling theorem. Okay, first we'll understand the second option which is available to us, then we'll move on to the third option in upcoming sessions. Okay, let me take with the case 2 or the option 2. Okay, the option 2 says that the sampling rate must be twice of its bandwidth, and we can call this as simply as 1 over t for our substitution in for the steps in the process. And we can note that there would be in turn two cases in this option 2. Okay, so there would be in turn two cases, two sub cases. So okay, if you can carefully note, the first case would be, okay, the first case what would consider is the upper frequency could be something integer multiple of the bandwidth, or it need not be. The upper frequency that you have considered for a bandpass signal could be an integer multiple of the bandwidth b itself. So that could be one of the cases where k is any integer. Or otherwise, the most generic case here would be fu need not be an integer multiple of b. We will understand these two cases when applied to the bandpass signals. Let us quickly take the first case where fu is an integer multiple of b. Okay, and since we have seen that the bandwidth is defined as fu minus fl, which is the difference between two frequencies fu and fl, this implies substituting fu as kb. So we can immediately see that fl can be written as k minus 1 times b by substituting fu as kb. Okay, now that we have expressed fu and fl in terms of the integer k and b, we can also write the center frequency fc, which is half of fu plus fl. Okay, which we can write by substituting this fu and fl in terms of k and b. We can write this as half fu is k times b, fl is k minus 1 times b, and this would give us k minus half times b. And note that b is 1 over 2t, because we have taken fs as 1 over t, which is twice of the bandwidth b, and hence b is 1 over 2t. Okay, now that we have seen, now we know that a real bandpass signal can be expressed in terms of its low pass equivalents. Okay, equivalent signals, and also we know that these low pass equivalent signals can be separated with its in phase and quadrature components, and hence from our basic discussion on earlier sessions, x of t can be written as xi of t, which is in phase component, times cos 2 pi fct minus xq of t times sine 2 pi fct. Okay, let us call this as equation 1 for our reference. And Now we need to take sample of this signal. Now substitute t as nt to convert this into discrete signal, or in other words we are taking the sample of this continuous wave. Okay, so x of substituting t as nt, so just replacing everything, so x of I of nt, and if you carefully note that we have written fc in terms of in terms of capital T here. So substituting that fc from this equation, we can write this as cos 2 pi. Okay, fc is k minus half times b, where b is 1 over 2t. So replacing that, k minus half, okay, times b is 1 over 2t, and cos 2 pi fc, t is that t we need to replace with nt as we are taking samples, minus similarly the quadrature component nt sine 2 pi k minus half 1 over 2t times nt. Yeah, alright, so we can cancel out a few terms here, so therefore now we can simplify this expression x of nt. Okay, now can be written as xi of nt times cos, okay, t cancels here, t gets cancelled, and what is left here, we will be left with pi n. Okay, pi n, k minus half, I'll try to rearrange as this as 2k minus 1 by 2, so 2 will be an extra term here in the denominator, which is 2k minus 1 by 2. Okay, will be left, t gets cancelled here, this will be the in phase component. Similarly xq of nt sine the same argument by n 2k minus 1 by 2. Okay, let us call this as expression 2. Now this contains even and odd samples, in the sense this we can separate. These are the samples which we can separate them into even and odd terms. Okay, we'll see how does even samples would look like. So even terms, in the sense we need to substitute this n as some even integer, where m takes all the values of integer, so n will take only the even integers. So with that we have defined t1 as twice of t. If you check back, we can substitute this t1 as 2t, where 2t we have considered it as 1 over 2b. Okay, where that 1 over 2 gets cancelled here, which is 1 over b, and I will be substituting wherever I find a 2t, I will be substituting as t1 as a dummy variable, you will see, which will simplify the representation of this even and odd terms. Okay, so with this, what will happen with this cos and sine arguments, that is what is important to us. Okay, so this argument of sine and cos, which is pi n times 2k minus 1 by 2, okay, what will this become? By substituting n as 2m, so 2 gets cancelled here, so this will simply become pi times m times 2k minus 1. Okay, so this seems to be an integer m, where m take all the values of integer, k also takes all the values of integer, but 2k minus 1 is an odd. So odd into some integer will always give an some other integer, so it is indirectly saying it's an integer multiple of pi. Okay, so if it's an integer multiple of pi, we know that sine of integer multiple of pi is 0. Okay, so what will happen to cos of integer multiple of pi? It will be simply switching between plus and minus 1. That can be considered by simple an method, where let us take couple of cases here. Say what happens to this value when m and k take different values, and I'll take this pi m times 2k minus 1 as alpha. Okay, and I'll try to find out what happens to this cos of this argument and sine of this argument. Let us take this takes some values, say 1 1 1 2 2 2 2 1 and 2 2. Okay, so if I take further higher orders of m and k, as we know that cos of alpha is uniformly distributed, in the sense alpha is uniformly distributed between 0 and 2 pi. So higher orders of m and k will just roll back in the in the space of 0 to 2 pi. So if we can find out the relation between m and k for cos of alpha and sin of alpha, then we are good to generalize for other values as well. Okay, so alpha for m and k is equal to 1. If you carefully note, this will be simply pi, and for m1 and k is equal to 2, we can say this is 3 pi, and for m is 1 and k is m is 2 and k is 1, so this will be 2 pi and this will be 6 pi. Accordingly, cos alpha, this is -1, this is -1, this is 1, and this is also 1, because these are integer multiple of 2 pi's. And for all the values of these alpha, sin alpha would be 0. So this means that this cos alpha, we can simply represent this as you can see, this is simply depending on the value of m. So whenever m is 1, this is -1 power 1, which is -1. So whenever m is 2, it is -1 square, which is +1. Okay, so this can be continued for other values of m and k, but this would be true for all the cases of m and k. With that, we can say that with this simple argument, we can simply state that therefore cos, okay, only cos terms will exist. Okay, only cos terms will exist. Okay, so this implies equation 2 now can be written as, okay, so equation 2 can be written for even samples as n is 2m here, where we have replaced we can represent twice of t as t1. So in other words, this is simply x of mt1, okay, so which is equal to xi of mt1, okay, times minus 1 per m, so which is nothing but -1 per m. Okay, let's call this as equation number 3. Similarly, we can do this for odd terms. Okay, what will happen to odd? So for odd, we need to replace n with odd values. Again, we will be substituting t1 as 2t and 1 over b. This need not be done, but just for ease of expressing these even and odd samples, this would be helpful. Okay, again the argument pi n 2k minus 1 by 2, what will happen to this? This substitution of n as 2m minus 1, this will be this can be rewritten as pi by 2, n gets replaced with 2m minus 1 and 2k minus 1. Okay, with similar argument what we have done for even samples, the same thing can be done for for odd samples as well, where we'll see what happens to cos of this argument beta and sin of beta. Okay, let me take similar approach what we had done for the previous. Okay, so m and k, let us take, it will take few values, 2 1 and 2 2. Okay, what is beta? So when m and k are 1 each, beta is simply pi by 2, and when m is 1 and k is 2, you can see that this is 3 pi by 2, this is also 3 pi by 2, and when both are 2 and 2, this is 9 pi by 2, and you can see yourself that for all values of this, because this is an odd integer multiple of pi by 2, so for all such values cos of beta is 0, and sin beta for sin pi by 2 this is 1, 3 pi by 2 it is -1, this is also -1, 9 pi by 2 it is pi by 2 again, which is your +1. Okay, so if you carefully note this table for sin of beta, we can replace this as -1 per m plus k. Okay, So when m and k has 1 each, so this is minus 1 squared, and it fulfills the first and last row of this table. And for other two rows, you can accordingly substitute, and you can verify yourself. Okay, so with that we can replace the equation 2, or we can say for odd terms only sign terms will exist, okay, which will be replaced with minus 1 per m plus k. So for odd terms, our equation 2, which has all the components, I mean all the samples, even and odd. Just for odd, this can be replaced with 2m minus 1t, which is nothing but x of 2mt minus t, and we have replaced t by t as t1 by 2, so this can be replaced as x of mt1 minus t1 by 2 in terms of t1. Okay, so this implies the odd term 2m minus 1 times t can be written as simply as xq times mt1 minus t1 by 2 times sine of all the arguments, and sine of that argument is we have replaced with m plus k. Let's call this as equation number 4. Okay, so equation 3 and equation 4 represent even samples and odd samples. Okay, and you are note that we are sampling x of t at a rate of twice of b samples per second, correct? And therefore the equations 3 and 4, which are even and odd terms, okay, so which in other words we can say that the samples will occur at a rate of half of this total rate. Okay, so this implies the low pass signal components, okay, low pass signal components occur at a rate of b samples per second. Okay, so that will obtain the samples of this bandpass signal. Now that we have obtained samples of this signal, our next part of this session is to verify whether we can recover the original signals, an original bandpass signal or not. Okay, so let's try to verify this with the reconstructing the original signal based on these in phase and quadrature samples, or even and odd samples. That means that x of 2mt and x of 2m minus 1t, okay, now be used reconstruct the equivalent low pass signals xi of t and xq of t. Once we obtained xi of t and xq of t, we can get back the original bandpass signals based on these signals, okay, respectively. All right, so what is xi of t? How do we try to reconstruct back? Based on our understanding in communication system 1 course, we will reconstruct the original signal back by passing these samples through a low pass filter and try to reconstruct the signal back. Okay, so we know that low pass filter has got rectangular response in its frequency domain. In its time domain, we can represent it as sinc function. So that it's just the convolution or the output of this low pass filter, as in the sense, say we'll pass this xi of xi of 2mt these are the samples in fact, and xi of 2m minus 1t through a low pass filter, and try to get xi of t and xq of t back, and hence together we can construct the original bandpass signal. Okay, so what I mean to say is the output of this low pass filter xi of t and xq of t are respectively the convolution of the input samples xi of 2mt and xi of 2m minus 1t with the impulse response of the low pass filter, where the impulse response of the low pass filter is that is sinc pi t over t. Okay, so therefore with this basic understanding we can write xi of t and xq of t as the convolution. Convolution runs for all the values of m. Xi of 2mt can be, we have written or represented as mt1 times sinc of h of t minus tau. Okay, so that is nothing but pi by t1 t minus mt1. Okay, and similarly xq of t, summing this for all values of m, xq of mt1 minus t1 by 2 times sinc of pi by t1 times t minus mt1 plus t1 by 2. Okay, let's call this as equation number 5. Okay, and from 3 and 4, okay, you can see that from 3 and 4 we have expressed x of mt1 and x of 2m minus 1 times t1, 2m minus 1 by times t, or x of mt1 minus t1 by 2 in terms of xi and xq. Now that we want the values of xi and xq, we can just take this minus 1 power m and minus 1 power m plus k to the other side and express xi of mt1 and xq of mt1 minus t1 by 2 in terms of the left hand sides. Okay, utilizing these equations 3 and 4, okay, using equations 3 and 4, we can write x of 2mt, okay, or I can write this as what we have, x of 2mt as minus 1 power m times xi of mt1. So this implies xi of mt1 is minus 1 power m x of 2mt. Similarly, we have x of 2m minus 1 times t, which is minus 1 power m plus k, xq of mt1 minus t1 by 2. This implies xq of mt1 minus t1 by 2 is minus 1 power m plus k times the odd samples x of 2m minus 1t. Okay, so substituting that back into our first equation, now we can reconstruct x of t using equation 1. So what is equation 1? So if you refer back, the equation 1 we have is x of t, where we represented bandpass signal in its in phase and quadrature components minus xq of t times sine 2 pi fct. So what is xi of t and xq of t? Xi of t is given by equation number 5, and in turn equation number 5, okay, is represented in this fashion. Let us call this as equation 6. So we can utilize equation 5 and 6 and substitute in equation 1. So we would get, we can write this as, okay, xi of t is, summation m varying from minus infinity to infinity can be taken out, and xi of t is summation of x I of mt1 xi of mt1 is can be substituted from equation 6. So utilizing both 5 and 6, this can be written as minus 1 per m x of 2mt times cos of 2 pi fct times sinc of pi by 2t. Now I am replacing t1 with t now, okay, because we have to get back to the original signal, minus 2mt. Okay, this is the first part of it for the even samples, minus, okay, minus 1 per m plus k x of 2m minus 1 times t sine of 2 pi fct times sinc of pi by 2t times t minus 2m minus 1 t. Okay, now we can, of course, the summation m is for both the terms. Now if you carefully observe, we can club in a few terms here. If you carefully observe, this minus 1 per m and cos 2 pi fct can be clubbed together, okay, and can be written, which can be simplified in this fashion. Okay, now that, okay, now this minus 1 per m times cos 2 pi fct can be replaced or can be written as cos of 2 pi fc times t minus 2mt. This is simple. We can prove this by utilizing our basic principle of cos a minus b expansion, basic principles of trigonometry, where this can be proved this way. If you consider cos of this term 2 pi fc times t minus 2mt can be expanded, okay, can be expanded as cos a cos b, which is 2 pi fc times 2mt plus sin a, which is sin 2 pi fct times sin b, which is 2 pi fc times 2mt. Okay, and we know that fc can be substituted. Now put fc, we know that this is k minus half times b, where b is 1 over 2t. So this implies this left hand side will become cos of 2 pi fct times cos, okay, this is 2 pi fc. I'll be replacing with this part half, where b is 1 over 2t times 2mt. Okay, similarly for the second half, where this is sin 2 pi fct times sin 2 pi times k minus half times 1 over 2t times 2mt. Yeah. Alright, so let's cancel few terms here. So, or otherwise we can just take this argument outside, and if you carefully look at this, this gets simplified to what? So t gets cancelled, 2 and 2 in the denominator also gets cancelled. So this will simply become m pi times 2k minus 1. Okay, so this is again cos of m pi times 2k minus 1 and sine of the same argument, which is m pi times 2k minus 1. which we have proved earlier that this is represented as -1 per m, and for all the m values of m and k this is 0. So this implies the left hand side, which we have replaced, I mean cos 2 pi fc, which is t times 2 pi fc times t minus 2mt, which will be equal to cos of 2 pi fc t, and this can be replaced with -1 power m, and the second part of this is 0, which is what we have replaced this term with. Okay, that proves the equivalence of the multiplication of these two terms. Similarly, we can also club these two equations, where these two parts of the equation, which is -1 per m plus k and sine of 2 pi fc t as, okay, so this -1 times m plus k times sine of 2 pi fc t as what? We can replace this as cos of 2 pi fc times t minus 2m minus 1 times t. We can verify yourself based on the expansion of cos a minus b again. Okay, so this is similar to the previous part that I tried to prove. So therefore what we have obtained, so therefore x of t now is summation m. Okay, so we have clubbed two terms here, so x of 2mt. So what is left in our this term? The first term will be cos 2 pi x of 2mt. This both terms we are clubbed together, and we have expressed this as cos 2 pi fc t term. So what is left here is x of 2mt times sinc of pi by 2t times t minus 2mt times cos of 2 pi fc t minus 2mt. Okay, this is the first part. Second part is x of 2m minus 1 times t sinc of pi by 2t times t minus 2m minus 1 times t times cos of 2 pi fc t minus 2m minus 1 times t. Okay, times t, and of course the summation is for both of the terms. Okay, so if you check now, the first part of this equation is even terms, the second part is just the odd term, so we can collapse these two terms into single summation. Okay, so collapsing this into a single summation. Okay, we get one term which is x of t, which is equal to summation m running from minus infinity to infinity x of mt, because this is just samples of x of t now, times sinc. Okay, so this is pi by 2t times t minus mt now, because even and odd terms are clubbed together, and similarly cos of 2 pi fc t minus mt, because again odd and even terms are clubbed together. Okay, so this is our reconstructed bandpass signal based on its samples. Strikingly, this reconstructed signal is very similar to what we had obtained using our low pass sampling theorem. Okay, so comparing with reconstructed low pass signal, okay, based on Same Nyquist theorem, because we have applied Nyquist theorem for bandpass signal here, where the sample rate is twice of the bandwidth. Theorem, what was it? So if I try to represent that reconstructed low pass signal based on Nyquist theorem, so that is g of t summation, n running from minus infinity to infinity, g of n by 2w, okay, sinc of, you can check this, 2 pi w t minus nt, okay, where w is the bandwidth of the low pass signal. Very similar to the reconstructed signal in our bandpass case, right? Only the difference which you can observe between these two reconstructed signal is that this is shifted at a center frequency of fc. Obviously that represents the bandpass signal, where it occupies the magnitude and phase spectrum at a center frequency not equal to 0. All right, so this we had called as interpolation formula. Okay, now we can conclude that our bandpass signal can be reconstructed faithfully based on our applying the Nyquist theorem, or if you take samples of this bandpass signal at a rate of Nyquist, based on Nyquist theorem, we can reconstruct the signal faithfully, reconstruct the signal back faithfully. Alright, this completes the first case of assuming. As you can see, we have assumed the upper frequency is an integer multiple of the bandwidth of the bandpass signal. So if you want to summarize this, okay, we can summarize this, the complete flow, what we did in today's session, that we considered a real bandpass signal, say x of t, and try to take sample at a rate of twice of b, which is bandwidth, all right, where we represented a dummy variable t1 as twice of t, just to ease our representation in the flow. The splitting of x of t, taking the samples of x of t can be separated with even samples and odd samples. Okay, so even samples and odd samples, where even samples were represented as 2mt. Here we represented this as by replacing n with 2m minus 1, and accordingly based on few equivalences we concluded that this is equivalent to minus 1 per m xi of mt1, and this is equivalent to minus 1 per m plus k xq of mt1 minus t1 by 2. So this apparently proved that the even samples of this bandpass signal is represented by its in-phase samples, and however the odd samples are represented by the samples of quadrature components. Okay, so after this we try to reconstruct the signal back. Okay, so then the reconstruction involved by taking this in-phase and quadrature components, getting back the original signal. So we try to pass through these in-phase and quadrature component through a low-pass filter whose impulse response, we took the convolution with its impulse response, where this was pi t1 times t minus mt1 for all m's. Here the convoluted sinc function was represented by minus 1 plus t1 by 2, and again we had even and odd terms. We tried to collapse this into single summation, and we got back the reconstructed x of t. So this was the flow in this today's session. So in upcoming session we will deal with what happens when fu or the upper frequency is not an integer multiple of its bandwidth, which is the second case in the option 2 itself. We will try to deal that, and finally we'll take the consideration of any sampling rates between these two extremities. Yes, thank you.